Well, please join us to this next speaker. His name is Sumanth Nirmal. He is the head of Middleware and Founding Engineer at Apex. So please welcome him and enjoy this session.
Thank you. So let me directly start by asking you a question. How do you think the future will be with humanoids all around us? Take a moment to think. Imagine it. Think about like humanoids as a coworker in the restaurant, at home, helping us, doing our tasks. So I asked the same question to the AI. It generated this video. So robots walking among us in homes, hospitals, cities. But this isn't just AI. If you look at it, Agility is promising to develop 10,000 robots in a year. Figure plans to ship like 100,000 humanoid robots over the next 4 years. Financial analysts are saying humanoids will be a 5 trillion market by 2050 with 1 billion robots. So humanoids is not sci-fi anymore. The scale is massive, the ambition is massive, but the age of humanoids is no longer science fiction. But is it really happening? You see all these videos on social media where robots can do all these impressive tasks, walk, run, Parker kind of tasks, even emptying your dishwasher in the house. But if you look at them closely, these are all filmed in tightly controlled, staged environments. Often these are heavily teleoperated. What you see is also maybe one of the best shots out of 100 attempts. If we remove this from staged environments, move to real world, you see them fail. The Optimus, this was an event in Miami. It was a completely autonomous event where it drops a bottle and then falls down. You can also see the movement where it is replicating the motion of removing a VR from its head. It's probably a teleoperation malfunction. On the right side, there's a digit from Agility Robotics, which is collapsing when it is trying to pick up a box. The truth behind this robot is this Agility robot has done, I don't know, maybe 1,000 successful pick and place. So genuinely, the robot might be tired, but still. When working with humans, if a robot falls, it's still not safe. Okay. So they fall, they freeze, they fail. They successfully work flawlessly in staged environments. But the moment you move them to real worlds, they are brittle. So maybe one more question. Have you seen this movie before? A technology which has managed to raise $1 billion, promised to change the future radically, and failed in reality? Of course, yes, autonomous driving. What did we see? Elon Musk promised we will have a fleet of 1 million Teslas in 2020. Reality, zero deployed. Ford announces plans for mass production of self-driving cars without steering wheel by 2021. Reality, they have shut down their autonomous unit Aura in a year. And we also saw similar failures. I think this is around 2017-18. The video down is from this company Phantom, where they are showing their technology to TechCrunch reporter. It was on a highway, driving at highway speeds, and the safety driver was unable to react at time, and it hit the car in the front. The video on the right is a semi-autonomous truck. It's a huge truck. It suddenly veered to left on I-80 and hit the divider because of some old malfunctioning code. So what did we promise? We promised autonomous fleets on every corner. We delivered zero. Instead, we fell into this trough of disillusionment. The previous talk before me talked about the hype cycle. So this exactly explains where we are also with humanoid. I say this about the hype cycle not as a critic, but I have experienced this myself firsthand. So my story starts in 2012, where I started with autonomous lawnmowers, first of its kind, world's first autonomous intelligent lawnmower from Bosch. We shipped this to 1,000 plus homes in 2012. This is low stakes. If it fails, it hits a fence, nothing happens. Consumer grade. This is when I was introduced to ROS and also saw the power of community around something like this. But then it also comes with chaos of how do you put a research code in consumer box. Then move to 2015, it's an agricultural beast. It's also an autonomous robot, helping like seed breeding, weed killing, phenotyping, etc. Super complex. We were already pushing the limits of navigation and control algorithms in unstructured, muddy environments. This is when I realized it's not all about the brains, intelligent algorithms. It's basically about a deterministic, safety-critical core on which you should build your products. That's when I moved to Apex.AI, where I'm currently working, and we built performance, safety, deterministic middleware, which is basically powering the world. So everything you see around, we have the software that I built is powering autonomous tractors running in the field. There are these huge boats with auto docking and parking. It is being used in robotaxis. So I have seen this all the way from high-level algorithms to low-level safety-critical middleware, all the way from consumer-grade autonomous systems to super safety-critical, life-dependent autonomous systems. The thing I have learned, sorry. The thing I've learned is if there is one thing, advanced algorithms are useless in the real world if you really don't have a deterministic performance safety critical middleware. So we have, let's go back to this hard question. So we have all these nice videos. We know that the technology is there. Robots can move. They can do all this fancy tasks. But the real hard question is, why don't we still have them in our homes, doing our laundry, helping out with our mundane tasks? What is the missing link? Is it the hardware? Of course, yes. But as you see, we are moving towards these super reactive, costly direct drives, electric motors. I think the arms and hands at the current day is almost reaching human dexterity. What else is the missing link? It could be reliable uptime. So the batteries are super short, but still, the industry, we are trying to find new fast charging technologies, new battery charging technologies, hot swap batteries. So the industry is working on this topic. General purpose brain, of course, most of the VC money is probably in this area. Foundation models, world models, vision language action models, general purpose foundation models. We need this general purpose brain to really generalize robots across tasks, across environments, basically in real world chaos. But there is still one crucial thing that is missing, which is a safety critical middleware. I call this as nervous system. You could have the most smartest brain, you could have the best muscles, but if your spine is not great, then you will basically not move. So safety critical middleware is the one that is bridging everything together and making sure that whatever this smart, intelligent brain commands, that it executes, guaranteedly executes safely, reliably, and instantly. So from here on, I will focus on this middleware part. And convinced that this is also one of the crucial link that is missing to scale humanoids to real world. All right, to really understand what is needed to build such a middleware, we need to look at how the robotics stack looks like. So this is how a classical humanoid robotics stack looks like. You have an array of sensors, cameras, lidars, IMUs, encoders, force sensors. You get data from all these sensors. You feed this into your perception localization modules where you detect what is there in front of you. You basically localize yourself within the world. You plan your footsteps, you plan your path, how to move. Then you have this heavy math-based, model-based control algorithms, MCP, ZMP. Anybody doing classic robotics should be familiar with this stack. And then you actuate the commands to motors. This is how it works. So everything is handcrafted. This is rigid. Everything is modeled. You should model every behavior. If the robot encounters a new behavior, like it steps on ice and you are modeling doesn't consider this, then it basically fails. We could draw same parallel to autonomous vehicle stack or autonomous driving vehicle stack. Usually the industry, it's called AV 1.0. It's the same thing. On the high level, you have sensor, perception, planning, control. So it's basically the sense, plan, act pipeline. This, as I said, this stack is rigid, written in C++. Every behavior you have to model. It cannot generalize. And every block, you have an arrow that is moving data from one block to other. So classic middleware focus on data plumbing between fixed parts. Because this will not generalize, industry is moving towards AI native stacks, and that's how it looks. So we are replacing these rigid models with end-to-end learning model. There are different ways how to solve this, but I chose this. So it's a two model-based approach. So slow thinking and fast thinking. This is what the industry is called. So you have a slow model, which is vision language model, which is understanding the world, understanding where the robot is, semantically making sense of the data, breaking down the task that it should perform. And then there is a fast reactive control, which is a diffusion transfer model. This basically replaces all the hardcore math control in the classical stack. So this model learns the physics by training. Yeah, exactly. And then it can predict the outputs. You have a safety limiter, which makes sure everything is safe, and then you actuate. We can still draw the same parallel to AV stack. The current AV stacks, AV 2.0, most of the AV companies are moving to this, is pretty similar to what I showed is on humanoid stack. So you have a sensor, you have an end-to-end learned policy, you have a control which will actuate your car. So what this means is we are moving towards stacks where neural networks are its at core. So we need a middleware that is capable of moving humongous amounts of data, and the volumes of data will only grow as the models will generalize. So what do we need to support these kind of AI native stacks? So I broke down the features of middleware into 3 pillars. So the first pillar is extreme performance. So an AI native system like humanoids or autonomous driving car that basically has an end-to-end learning model has like an array of sensors. It doesn't matter what is the embodiment, but the stack and the high-level approach is still the same. You have multiple sensors, everything talks in different protocols. So the middleware should be able to extract these protocols, generate a unified timestamp data stream, which the models can use with. So that's one part, protocol abstraction. And then the key part for performance is zero copy. The traditional middlewares or typical zero copy solves the problem of inter-process communication. But the moment you start speaking with AI native systems where neural network is at the core, you also need a zero copy between your compute clusters, like CPU cluster, GPU cluster. And with the industry moving towards unified memory pool architecture, this only becomes more important. So zero copy, transport, unified data stream, protocol abstraction are the key for performance. So the next pillar is deterministic execution. This is one of the hard engineering problems to solve for middleware, because AI native system executes different components at different frequencies, different criticality, different safety levels. You could have an AI policy which is like understanding what the world is doing. It doesn't matter if it takes 2 milliseconds late to realize that you are asking it to pick up a spoon rather than a ball. But you have control loops which are actually commanding the actuators, which run at fixed rates. It has its own deadlines. It has its own latency budgets. How do you make sure that you run both on the same system without the non-deterministic part affecting the safety critical part? The answer is in the mixed criticality. So the middleware should support mixed safety criticality. What it means is the non-deterministic components should not affect your deterministic parts. This is usually solved by like having memory abstraction and then deadline-aware adaptive execution policies and all this. So for deterministic execution, we need mixed safety criticality, and usually for AI native systems, most of the inference runs in user nodes, which means no control of how much time does it take, no latency budgeting, no deadline policies. So middleware should also have some kind of inference engine abstraction. So you could switch inference engines at runtime, and you would also provide latency budgets and deadlines for your inference policies. The third pillar, and the important one, safety. It's a hard truth that everything that AI systems or AI native systems predict cannot be trusted in at least physical and real world. So there should be something which will convert the AI predicted actions into safe thing, so which is typically called runtime guardrails. So the middleware should also support something like a pluggable runtime guardrails. It can be as simple as a rule-based check, making sure that your actuator torques and accelerations and stuff like this doesn't go beyond certain defined thresholds, or it could go all the way like you have a model which is learned about safety and it can detect anomaly detection. So how it runs is like you give all your inputs to the model, you ask it to do something, it predicts an action, then middleware runs it through the guardrail, make sure that it is within the safety boundary. If not, then usually it goes through a fail operation path, which gives you minimal maneuver operation, similar to what also autonomous driving does. And then you always get safe outputs to the robot. So this will also allow us to safety certify your runtime guardrails, which will make sure that your robot is always safe without even worrying about how to certify a black box AI model. Okay, how does this look visually? So if you do something with the ad hoc system, it looks something like this. You have sensors, you have task description, you have a model which is trained on data. You feed this into the model, then the model predicts some outputs. But the model could predict a valid action, an unsafe action, and invalid action. If you don't have something here, and you directly send this to actuators, and the robot is working with humans in the real world, then it's not safe. How does this look with a middleware that is purposely built for AI native systems? So you have an inference runtime, which will abstract away your inference engines. This could also optimize which engine to pick based on the model, based on the compute, et cetera. The runtime runs the policy, predicts actions, and then the runtime guardrails make sure that whatever the model predicts is converted into a safe action. So this is how we enable AI native systems without compromising safety. It's not just about robots, but the middleware should also solve the problem end to end. So it's about the workflow. We need a middleware that will power us all the way from collecting data, feeding it back to the model, train, eval, and then run your software in the loop test, hardware in the loop test, etc., and then optimize your model and then feed it back. So this is how an end-to-end a pipeline for an end-to-end AI native system looks like. The middleware, which we built at Apex.AI, called Apex.OS, enables this end-to-end pipeline for AI native models. Conclusion. So to conclude, we are witnessing a massive shift towards end-to-end learning, which does massive generalization. But we face a risk of hitting the same trough of disillusionment which almost killed the AV industry. The solution is a performant, safety-critical middleware, which is built ground up for AI native systems. So we are done with demos. Now it's time for deployment. But remember, humanoids will only scale if their software foundation is safe, deterministic, and built for AI native workloads. So let's turn black box AI into certifiable safety. Thanks.
Thank you so much, Sumanth. We have time for some questions. Does anybody have some questions for Sumanth? No questions?
I have. Was one of your previous slides the one related to safety, in which you had a plan and you had the prediction of what's going to happen, whatever the neural network in between this one. So so this is kind of related to safety, related to what you're going to do. But it's good also to have something which is reactive to potentially something else happening, like a car is coming towards you, is not part of your task. So you probably have it in mind, but it's not incorporated in the slide.
Sure, yeah, sure. So what I focused here is about safety at the middleware level, but what you're talking about is like a level above. Like you could also move such a runtime guardrail before your inference runtime, and you would already eliminate most of those. If there is a car coming, there's no point for you to move. You need to stop. So there's no need to do the whole inference loop, get from guardrail and then stop. So you could do something like this, yeah. Yeah.
Any more questions?
Are there any elements from like the hardware itself that you, like, if you're picking out different hardware components to fit into your middleware, do you adapt your middleware to fit the hardware, or do you pick the hardware to fit into your middleware?
Probably I didn't mention explicitly here, but we basically abstract RTOS on high performance compute. So if there is a hardware that we need to support, we will add the abstraction for this. So as a middleware, we basically abstract away all the hardware complexity. And then the inference engine, of course, will be tied to what kind of compute you're using, how do you optimize the model for this compute and stuff like this, yeah.